Hello and welcome to the next lecture in this course on signals and systems. So we were discussing about the various system properties, and we have discussed namely the causality property, stability, time invariance, invertibility. So these are the different problems that we already discussed in our previous lectures. Now uh, today we will discuss the next property of the system, and that is linearity. Okay, so just to start, uh, the definition for a linear system is that if a system is linear, then the superposition principle can be applied. Okay, so this is the basic definition of a linear system, or you can also call it to be the condition for the linearity for a particular system, that if a system has to be linear, then it must follow the principle of superposition. Okay, so if the system is linear, then what does it mean? It means that superposition principle can be applied. Now the next question arises, what is this superposition? So superposition simply implies that the response or output resulting from several input signals can be computed as the sum of the responses resulting from each input signal acting alone. Mathematically, the superposition principle can be explained or can be stated in this form, that you just suppose that for a particular system, if a particular input is x1t and the output for this input is represented by y1t. So this is for a continuous time system. If the input is x1t and the corresponding output is y1t, and similarly for any other input for the same system, if the other input is represented as x2t and the output for this particular input is represented as y2t, then the system is linear. Then the system is linear if the response or output to x1 plus x2 is y1t plus y2t. Okay, so you can just write down that the response to this input x1t plus x2t should be equal to y1 plus y2. And one more thing is that the response to any particular input a x1t, where a is any scalar or constant you can say, then the output should come as a y1t. So whatever constant value is the input multiplied with, the output will also be multiplied with same constant value. That is the condition for linearity. So this first property which you have seen written over here is actually called the property of additivity, whereas this second property, this is referred to as property of homogeneity. Okay, so in superposition property, actually two different properties are there which should be followed by a system in order to be a linear system. Now we can just combine these two properties or these two statements in a single sentence or single statement, and then it should be that let us suppose if this is the input, you say, then the corresponding output should be so this is for a continuous time system. Okay, so where this a and b, they are some constants, so for a particular system to be linear system, this particular condition has to be followed, which is nothing but the principle of superposition. Okay, so x1 and x2 are two different inputs, and y1 and y2 are the outputs corresponding to the inputs x1 and x2 respectively. So when a system violates or it does not follow the principle of this superposition, then the system will said to be a non-linear system. Okay, so in order to just check the linearity for any system, we just have to check that whether this system is following the superposition property or not. If it is following the superposition property, for which you have to check both these additivity and homogeneity property. So if a system is following these properties, then it is fine, we can say that the system is linear. Otherwise, if the condition is violating, then we can say that the system is non-linear. Okay, so this is the meaning of this linearity property. Now we'll try to solve some examples based on the linearity. This is the first one, yt equals to txt. The question is that for the input output relationship of a system which is shown here, determine whether the corresponding system is linear. Okay, so this is the input output relation of a system, and you have to determine whether this system is linear or not. Okay, so you can just start your solution by assuming two different inputs, x1t and x2t. Okay, so corresponding to this x1t, the output is represented by y1t, which is nothing but t times x1t. So this is according to the relation which is given in the problem, because yt is given as txt. So for any input x1t, if the output is represented by y1t, so y1t can simply be written as t times x1t. Similarly, for some second input like x2t, if the output is represented by y2t, then the same output can be written as t times x2t. Okay, now you consider one more input and just assume that the output corresponding to x3 will be y3, and this will be represented as t times x3t. Now you assume this x3 as the linear combination of x1t and x2t. So that means that x3t you can just assume as the linear combination, that is a x1t plus b x2t. Okay, so this is the assumption where a and b are some arbitrary scalar values. So for following the property of linearity, or we can say that if this system is linear, then it must have to follow the principle of superposition, and principle of superposition means that for this third input the output should be a times y1t plus b times y2t, because you have assumed this third input to be the linear combination of first and second inputs. That is why the output for this third input should be a y1t, because y1 is the corresponding output of x1 and y2 is the corresponding output of x2. So this is nothing but the superposition property, you can see, and it contains both the additivity and the homogeneity, or scaling you can also say it. Okay, so now you just have to check that whether this condition is following or not, whether both the sides of this condition, both the sides of this equation, they are equal or not. So you just start with the left hand side of this equation and try calculating y3t. So y3t is nothing but t times x3t, and in place of x3 you put a x1t plus b x2t, because that is what you had assumed previously, that x3 is the linear combination of this. So you just simplify this expression, so this is nothing but a y1t plus b y2t, because t x1t corresponds to y1. Okay, so that we have already seen in the previous slide. So this is equal to the RHS, and we have started from the LHS of the equation. So now it is very easy, you can say that since the left hand side is equal to the right hand side of this equation, so this means that the given system is linear. Okay, so this is how it will be solved. You take one more example. In this second question, yt is given as x square t. Okay, now again the question is same, that you have to check whether this system is a linear system or not. So you just start in the same way, consider two different inputs x1t and x2t. So corresponding to x1 the output will be y1, which is nothing but equal to x1 square t. Similarly for x2t the output is y2t, and it can be written as x2 square t. Then you take one more input represent its output as y3 and then write the expression for the output according to the relation which is given in the problem. Then you just assume that x3 is the linear combination of x1 and x2, so it can be written as okay, so you can also write bracket here, x3t will be equal to ax1t plus bx2t, where a and b are some scalar. So if the system is to be linear, if the system is linear, then the superposition property should be followed, and that means that this y3t should be equal to a times y1t plus b times y2t. Okay, so again you just proceed in the same way. You start from the LHS of this equation. So y3t equals to x3 square t, and in place of this x3 you can put this value, and it should be whole square. Now you can just solve it, open the bracket, so this first term can be written as y1t because this corresponds to y1t. Similarly, this second term can be written as y2t plus this part we cannot replace it. So now from here you can see that this expression which is coming here, this is not equal to the RHS of the equation, you can say. Okay, so that means since LHS is not coming equal to RHS, we can say that the system is non-linear. Okay, so this is how the problems like this will be solved. Now we will consider one problem that will contain all the properties that we have discussed up till now. Okay, so let us suppose this problem yt equals to 0 for t less than 0, and it is xt plus xt minus 2 for t greater than equal to 0. So this is the input output relationship for a system. So for this system you have to determine, you can just write this question, determine whether this system is memoryless, stable, causal, linear, and time invariant. Okay, so all the 5 properties which you have studied up till now for systems, you have to check all the properties for this system. Okay, so we now start its solution. First of all, we have to check whether it is memoryless or not. So from the input output relationship which is given here, we can see that this system has memory, since the value of the output signal at any time t depends on the present and one past input signal xt. Okay, so you can see that yt consists of xt plus xt minus 2. Okay, so this t minus 2 actually is the, you can say, the past component which is present in the output, and that is why we will say that this system has memory. Okay, so that means it is not memoryless, it is having some memory. So from the input output expression we can just see, if it is, if the question, if the expression in the question was yt equals to xt, then we can say that the system is memoryless, because the output at any particular time t will depend on the input at that very particular time instant. But this t minus 2 instant is actually fast as compared to the t, and that is why it can be said that this system possesses memory. Okay, so the first part is already solved. Okay, you can, this was the first part. Now in the second part, we have to check the stability of the system. So for checking the stability, you first assume that the input xt it satisfies this condition, that means it is bounded. Bx is any finite value which is less than this infinity. This thing we had discussed when we were discussing the stability. So let us just assume that xt is a bounded, you can say, finite value. Now output, the magnitude of the output, so for t less than 0 it is 0, and for some t greater than 0 time xt plus xt minus 2. This is what is given in the problem. Okay, so this whole thing actually it is either less than or equal to t less than 0 magnitude taken separately now. Okay, for t greater than 0, so this should be less than or equal to okay, so this is quite obvious since we have assumed the magnitude of xt as bx. So the magnitude of output will be either less than or equal to this twice bx value, whatever be the value of this bx. So what we conclude from this is that if there is any input, if any input is bounded by any arbitrary positive number bx, this bx which is shown here, so if any input is bounded by this positive number bx, then the corresponding output is also guaranteed to be bounded, isn't it? So we have seen here also that the output is coming as twice of bx, so this will be also bounded. So that means that it is following the condition of stability, and this means that the given system is stable. So you can write down here that for this system, if input is bounded by bx, which is any positive number, the corresponding output is guaranteed to be bounded. Okay, and thus it will means that the system is stable. Okay, so this was the second part. Now you come to the third part, that is checking the causality. So again you can just see from the expression which is given in the problem that this system is a causal system, since the present output yt at any time t depends on the present and past values of the input signal xt. So you can just write down that present output yt depends on present and past values of input xt, and that means that the system is causal. Okay, so we have finished this part as well. Now for the fourth part, that is for checking the linearity. So you can just proceed in the same way as we had just solved few of the problems, like you just assume two inputs, first x1 and x2. So for input x1 you write the whole expression again. Input will be x1. Okay, and similarly for x2 the corresponding output will be y2. You can write the same expression again, just replace x1 with x2 here. Okay, and similarly for x3 the output will be y3, and again you can just write down the same expression here and just replace here x with x3. Okay, and similarly as we had done in the problem related to linearity, so you assume this third input to be the linear combination of first and second input. Okay, so this is what you have to do, where a and b are some scalars, then yt should be equal to a y1t plus b y2t. Okay, So this is obviously the condition for linearity. Okay, now you consider the left hand side of this equation. y3t equals to 0 and x3t plus x3t minus 2. This is for t greater than equal to 0. This is for t less than 0. Okay, so 0 for t less than 0, it will remain same, and in place of x3 you can put a x1t plus b x2t. Okay, so and similarly in this second part, in place of x3, so it will be a x1t minus 2 plus b x2 t minus 2. So this is for t greater than equal to 0. So again you just write down the step, and for this second part you have to do some rearranging in the terms. So a you can take common, okay, so a and b, they can be taken as common. So from here you can see that this is nothing but a times y1t, because this x1t plus x1t minus 2, this is y1t, and the second, this x2t plus x2t minus 2, this is y2t. Okay, and this will be equal to this RHS. So that means that the given system is a linear system. Okay, so you can just write down that the system is a linear system. Okay, then the last part is to check the time invariance property. Okay, so for checking the time invariance property, again you just take any arbitrary input x1t. So the output y1t will be equal to 0 for t less than 0, and x1t plus x2t minus 2 for t greater than equal to 0. It should be the corresponding output for input x1t. So this is any arbitrary input you have assumed. Now for checking the time invariance property, if you remember that we used to consider a second input which is obtained by shifting x1t. So now consider a second input x2t which is obtained by time shifting the first input. Okay, t minus t naught. So the corresponding output y2 will be x2t plus x2 t minus 2. So if you put the value of now xt, so it will be x1 t minus t naught plus x1 t minus t naught minus 2. Okay, so this for t greater than equal to 0. Okay, now consider again this y1t x1, this will be x1 t minus 2 for t greater than equal to 0. So from here you have to obtain y1 t minus t2. So the procedure is same as we had discussed for the time invariance problems when we were discussing the time invariance property. Okay, so in place of t you can just put t minus t naught. So t minus t naught will be here as well, and t minus t naught will be here as well. Okay, so you can just simplify now this expression, t less than t naught, and this will be x1 t minus t naught plus x1 t minus t naught minus 2 for t greater than t naught. Okay, so now what you see from here, that y2t which you evaluated in the previous step is not the same as this shifted version of y1 t minus t naught. Okay, so you can just see the difference. So you can write down, since y2t is not equal to yt minus t naught, then it means that the system is not time invariant system. So if the system is not time invariant system, it means that it is a time varying system. Okay, so now we have completed all the different properties related to systems, and we have tried to solve the problems based on each property. And this last problem which we just discussed, it consists of all the different properties. So with this much, actually this unit also it comes to an end, and in this unit we have developed a number of basic concepts related to the continuous and discrete time signals and systems, and there are several examples that were discussed. The mathematical representation of signals and systems were also discussed, that we will use throughout the course, the remaining content of the course which is left. And specifically, if we say that we introduced the graphical and mathematical representation of the signals and used these representations in performing the transformations of the independent variable. Okay, so and we also defined several basic signals both in continuous time and discrete time, like for example the complex exponential signal, sinusoidal signal, unit impulse, step, ramp, all these type of signals we discussed. And we also discussed various properties. We also discussed like periodicity and all the other things as well for continuous time and discrete time signals. Okay, so we also then in the next part, after the signals, we discuss the you can say systems, the ideas related to systems, and the number of important properties of systems like the stability, causality, time invariance, linearity. Okay, so now after discussing both these properties, one important point I would like to tell is that these two properties, that is the linearity and time invariance, they constitute important properties. Okay, and the systems which follow both these properties, that is linearity and time invariance, that is those systems which are linear as well as time invariant, these systems are collectively called the linear time invariant systems. Okay, so in short they are called LTI systems. So LTI systems actually they are an important class of systems, and both in continuous time and in discrete time. These systems play a particularly important role in the system analysis and design, uh, in part due to the fact that many systems encountered they can be successfully modeled as the linear and time invariant. And further, as we will see in the remaining units, that the property of the linearity and time invariance, it will just allow us to analyze in detail the behavior of LTI systems. Okay, so whenever a system possesses both the linearity and time invariance property together, it is called a linear time invariant system or LTI system. So we will throughout the rest of our discussion in this course, we will frequently use this term LTI system. Okay, so with this much we stop today, and then hopefully in next class we'll start our next unit. Thank you very much.